To this point in the class, we've really classified reactions mostly by the actions that take place among the nuclei of the reactant species. For example, we use the term proton transfer to describe a reaction where a Bronsted acid donates a proton to a Bronsted base. An addition is a reaction that joins nuclei that were initially separated, and then, of course, an elimination reaction is the opposite, right? So we're going to break apart those nuclei. In a substitution, one or more nuclei in a given species are replaced. But reactions can be classified in lots of different ways. They can also be classified as reduction, oxidation, or redox reactions. If there's a transfer of electrons from one species to another. And of course, we went over this in general chemistry, and it still applies through organic chemistry, and it'll continue to apply through biochemistry. So we're going to begin this chapter by learning how to determine whether a reaction is a redox, and that's really just going to be a little bit of a review. And we'll see that some of the reactions we've previously studied are also redox reactions. And then we're going to learn some new redox reactions that really help out in synthesis. Now, some of the most useful redox reactions involve organometallic reagents. And I love these reagents. I think the chemistry they do is super fun. I focused on this in my personal undergraduate research. And so I think they're really cool. So when we talk about organometallic reagents, these are reagents that include metals, okay? So we're going to talk about reactions where organometallic reagents are produced, but then also reactions that organometallic reagents undergo. So what do they do? So we're going to talk a lot about famous or familiar organometallic reagents, like Grignard reagents, which we've already talked a little bit about before, alkyl lithium reagents, and lithium dialkyl cuprates. We're also going to learn some new reactions involving organometallic species, which are really useful in generating carbon-carbon bonds. Because if we can generate carbon-carbon bonds, all of a sudden now we can start building bigger molecules. Now, in general chemistry, you learned about a redox reaction, and that stands for reduction oxidation, and it's a reaction that involves a transfer of electrons from one species to another. And so there's nothing really new here. This is just a review. And a redox reaction can be identified by changes in the oxidation states of atoms in the reaction. And that's what we learned in general chemistry. But there's another way that we can identify this. So when an organic species is reduced, it gains a carbon-hydrogen bond or loses a carbon electronegative atom bond. An organic species is oxidized when it gains a carbon electronegative atom bond or loses a carbon oxygen bond. Now, let's talk about this electronegative atom here. It's an atom that is kind of more electronegative, and that would be things like oxygen, okay? And so I want you to look at the example here where we have a carbon to an oxygen, and we're going to lose, when we form the alcohol with sodium borohydride, we lose one of these bonds. No longer do we have a double bond, that's a single bond. So we're going to lose one of these. This is oxidation. Sorry. We're going to lose one of these. This is reduction. This is oxidized in this reaction, right? So remember, if this is reduced, it's the oxidizing agent. And then if this is oxidized, it's the reducing agent, okay? So remember those two kind of backward definitions there. And I'm just going to write, because I just want you to remember this, the reducing agent, right, is the species that causes the reduction, right? And it's oxidized, okay? And then, so whatever's oxidized is the reducing agent because it causes the reduction. And then whatever is reduced is the oxidizing agent because it causes the oxidation. So in this particular example here, sodium borohydride is oxidized. So it is the reducing agent, okay? And so when we talk about sodium borohydride, it's the hydride that does the chemistry there, like that. So we can even go a step further and call this a hydride reducing agent, okay? And so this entire reaction is an example of a hydride reduction, and that's how it can be classified, okay? This reaction here, lithium aluminum hydride, can also be classified as a hydride reduction because it's the hydride here that's the reducing agent. So these previous reactions that we've seen are hydride reductions, and they can be defined based on oxidation reduction kind of terms. Now, hydride reductions aren't the only type of reaction where an organic species is reduced. Let's look at a catalytic hydrogenation reaction. So here are catalytic hydrogenation reactions. These were first presented in way back in chapter 13. And I want you to notice that we end up with 2 carbon-hydrogen bonds that made up, of course, this initial double bond. And so when we look at this, we've added those carbon-hydrogen bonds, and so this is a reduction. Another reduction that we have encountered before is the Wolff-Kishner. Which is shown here in equation 24. In this case, both the carbon-oxygen bonds of the carbonyl group are lost, and 2 carbon-hydrogen bonds are gained. And so we would also define this as a reduction. The hydrogen there in this top one, right, is the reducing agent, or it's what's oxidized. And then the amines here, right, this particular molecule, are also the reducing agent, and they're what's oxidized as well. Now, so we've seen some examples of reductions, and so I bet the burning question in your heart is, are there examples of oxidation reactions? And yes, that would be correct. So an example of an oxidation reaction is epoxidation. Now, I do want to back up and say, we know if there's a reduction happening, there has to be an oxidation. So in organic chemistry, what generally happens is people are kind of looking at what happens to the molecule with the functional group, right? So we classify these by what happens to the molecule in the functional group as oxidation or reduction. So even though this is what's going through oxidation and this is reduced, we're going to call this an oxidation because it's what the functional group's undergoing. So that's just kind of a small thing about how these are classified. Now, right, we saw this type of reaction in chapter 13, and what we see here are we have gained 2 carbon-oxygen bonds, right, from this double bond. Now, as I mentioned before, just as the reducing agent can be viewed as the species responsible for causing reduction, right? Now we have an oxidizing agent, right? And this is viewed as the species responsible for causing oxidation, right? And it is the species that is reduced, because you can't have one without the other. So, not all reactions, though, are oxidation-reduction reactions. And so we kind of have to be careful here. So in addition to recognizing reactions that are reductions or oxidations, it's really important to recognize when a reaction is not a redox at all. So, for example, let's look at this nucleophilic substitution reaction right here. The only change in bond is to go from a carbon bromide, kind of carbon bromine bond here, to a carbon chlorine bond. Both bromine and chlorine are more electronegative than carbon, so the number of carbon electronegative bonds remains unchanged. So this is not a redox, right? Because we're not changing the number of carbon electronegative bonds. In equation 27, what we're doing here is we're adding water across a double bond. Even though this reaction produces a new carbon-hydrogen bond and a new carbon-OH bond, it's not a redox reaction. So, because, sorry, there was a dog barking in the background, so I had to look sternly at him. So it's not a redox reaction because we do form a new carbon-hydrogen bond, but we also form a new carbon electronegative atom bond. And so the idea there is those kind of cancel each other out. Okay? And so because these cancel each other out, it's also not a redox reaction. So we have to be careful. Not everything is a redox reaction. So I want us to do an example, right? Determine whether the following acetyl formation is a redox reaction. If it is, does the transformation represent an oxidation or reduction? So when you go through a question like this, here are some things you should ask yourself. Does the organic species gain or lose any carbon and hydrogen bonds? So all the carbon-hydrogen bonds that are part of the cyclohexanone are going to remain intact, right? And all of the carbon and hydrogen bonds in the CH3OH also remain intact. So the reaction does not change any carbon-hydrogen bonds. Okay. So then the next question we ask ourselves is, does the organic species gain or lose any carbon electronegative atom bonds? And so right here, right, we have two carbon electronegative atom bonds. And over here, right, we still have two carbon electronegative atom bonds. All right. So, right, the reaction doesn't change the number of the carbon electronegative bonds either. So no change in the carbon electronegative atom bonds. So, so the next question you need to ask yourself is, can we conclude from the number of carbon, hydrogen, and carbon electronegative atom bonds, what can we conclude from these numbers in the reactant and the product? Well, there's no change to the carbon-hydrogen bonds, and there's no change from the carbon electronegative atom bonds. So this sucker is not a redox reaction. So when you're asked to identify something as a redox reaction, you really need to analyze how the bonds are changing, right? And you need to see if there's a difference in carbon-hydrogen bonds and a difference in the carbon electronegative atom bonds. Now, in chapter 13, we learned that an alkene can undergo catalytic hydrogenation when treated with hydrogen gas in a metal catalyst. And the metal catalysts that we learned were nickel or platinum or palladium. Okay, and you can see an example right here. So this is that catalytic hydrogenation. And from just what we said, we know this alkene undergoes a reduction in this type of reaction. And so when it undergoes the reduction here, we form the alkane. So we go from an alkene to an alkane. Now, when we have a triple bond, right, and we have this in excess, we can go from the alkene, and if it's in excess, all the way down to the alkane. Okay, so we can go through 2 functional group changes here. Now, a lot of times it's advantageous to stop the reaction right here. And one of the ways to do this is a poison catalyst. And the poison catalyst that we talked about was the Lindlar catalyst, and it will stop it here in the cis alkene stage. And so that's a really helpful way to stop it. Now, here, so we've reviewed that a little bit, right? We've seen this before, but here's some additional information. Catalytic hydrogenation is not just limited to alkenes and alkynes. A variety of other functional groups can also undergo catalytic hydrogenation. And so pay attention, though, to the typical experimental conditions they require. Okay, so these are typical. So if you go from an aldehyde to an alcohol, it takes place under pretty decent conditions here, right? It adds like we have H2 and platinum's used as a catalyst. You can go from a ketone to an alcohol with hydrogen gas and using rhodium as a catalyst, and the temperature increases and the pressure increases, right? Just a little bit. So remember, like, normal pressure is 1 atm. So we can look at a nitrile group here, and we're going to use a catalyst called Rainy Nickel, which was developed in Chattanooga, Tennessee, so right down the road. And you're able to see here, right, how it's reduced. And then you can use platinum, and look at look at the pressure here. It's 200 atm and 250 degrees. So high temperature, high pressure. We go from an amide to an amine. And so notice that these conditions kind of gradually get a little harsher, right? Or a little harder. You know, we have to increase the pressure, we have to increase the temperature. It's because these other functional groups right here, right? These guys are more difficult to reduce, okay? And it's particularly true for the reduction of the amides down here, right? Because the product amine that we get here, that amine group, it poisons or deactivates the metal catalyst. So if you force the reaction by increasing the temperature and pressure, then the risk of unwanted side reactions increases as well. So, you know, there's always kind of this give and take. Now, because the catalytic hydrogenation of various functional groups can require very different reaction conditions, we often use catalytic hydrogenation to carry out a selective reduction. And so what we mean by this is alkenes, alkynes, and aldehydes are reduced under mild conditions. So basically we can say the functional groups that characterize alkenes, alkynes, and aldehydes can be selectively reduced when functional groups that characterize ketones, nitriles, and amides are also present. Okay, so I want to write that down for you. The functional groups that characterize alkenes, alkynes, and aldehydes can be selectively reduced when functional groups that characterize ketones, nitriles, and amides are also present. So basically, it's a pretty safe bet, right, that if you have a double bond here and a ketone here, this guy requires so much like pressure and temperature that he's really not ever going to be reduced, okay? And so we can use this and say, hey, look, this double bond is going to be reduced before this is ever going to be reduced, okay? The other thing that we see with reductions is that steric hindrance can also be used in a selective reduction using catalytic hydrogenation. So in equation 2013, we have two double bonds, but what we see here is the one that's less sterically hindered is selectively reduced compared to the one that's more sterically hindered. So in general, we can also say here, right, that catalytic hydrogenation is more favored at less sterically hindered multiple at, let's say, at a less sterically hindered multiple bond than at a more sterically hindered one. With more bulk, steric bulk surrounding the double bond, it's just more difficult for the alkene to absorb to the surface of the metal catalyst. And that's a critical step. So what we're saying is, hey, look, when this molecule comes in contact with this solid catalyst, this is more likely to come in contact with the solid catalyst because it's less sterically hindered. This over here is, I think I said that backwards, so I'm going to say it one more time. This is more likely to come in contact with this catalyst because it is less sterically hindered. This is less likely to come in contact with this catalyst because it is more sterically hindered. And the double bond has to touch the catalyst for the hydrogenation reaction to go or to work. I want to point out limonene here, which is the molecule we're talking about here. It's a monoterpene that occurs naturally in the rinds of lemons and other citrus fruit, like oranges. And so depending on where our labs fall, we are going to isolate limonene from oranges at some point. So there we are.